Hello friends, it's MoNaCo here. We're in our fifth lecture in organic chemistry. We're going to be talking about functional groups today. Up until this point, we've studied what carbon does, how it can make chains, rings, networks, how it can form hydrocarbons in chains that can then contain branches or double bonds. And so at this point, we have to take the next step up in the level of complexity and understand what a functional group is and how to identify it. Um, Basic nomenclature associated with that, like naming and drawing the compounds. And then we're going to begin drawing some organic compounds that contain functional groups in this particular lecture. So hydrocarbons and isomers of them can only provide a basic complexity to organic compounds. Are there any other elements involved in organic? So up until now, we've just done carbon and hydrogen. Now we're going to throw in all the other elements that can be in an organic compound. They're all nonmetals. Oxygen, nitrogen, halogens like chlorine, fluorine, bromine, iodine, are all capable of doing covalent bonds with carbon. And when you get one of these atoms attached onto your hydrocarbon chain, it's no longer a hydrocarbon, it becomes an organic functional group or an organic molecule. These groups cause the hydrocarbon chains to behave differently, giving new properties and new characteristics. So we're going to get a sense of what those functional groups are. It's an organic compound that forms when one or more hydrogens are replaced. An atom or group of atoms give the organic compound certain characteristics and properties. So that's a basic understanding what a functional group is. And the table R has a list of all the important ones that we are going to look at. So there's classes of functional groups, halides. So the halides have fluorine, chlorine, bromine, or iodine in them. We've replaced a hydrogen with one of those elements, and it becomes a halide, halocarbon. And alcohol, everybody's heard about alcohol. Well, alcohol is actually a type of compound, a class of compound with a functional group OH. So we've replaced a hydrogen on a hydrocarbon chain with an OH on the hydrocarbon chain. And ether. And ether is a different class. These used to be used as anesthesia in operating rooms. And in the ether, we've actually replaced a carbon in the middle of the chain with an oxygen. So it kind of replaced a carbon with an oxygen, and it's in the middle of the chain there. Aldehydes. People have heard of formaldehyde. It's one of the most simplest aldehydes, but that's another class of compounds. And this is when we've taken a carbon, and instead of filling it up with hydrogens, we've double bonded to an oxygen there and put a hydrogen on the end. These R's that you're seeing all stand for hydrocarbon chains. It could be any one, they could be one carbon long, they could be a million carbons long. They're just variables. Okay? A ketone. Ketones are not so common, but if you know somebody who's got severe diabetes, they might be susceptible to ketoacidosis. It's kind of a smell on the breath that you can tell somebody hasn't had their insulin properly. A ketone is kind of where you take a carbon in the middle of a chain and you take the hydrogens off of it and you double bond an oxygen to it. Organic acids, every time you have salt and vinegar chips, or any vinegar for that matter, you're ingesting an organic acid. It's an entire class of compounds where a carbon, the hydrogens have been taken off of it, and we've replaced them with oxygens, a double bonded oxygen above or below, and an OH group like the alcohol on the side, but it's not an alcohol because of the second group oxygen double bonded there. An ester is a class of compounds where we've taken some part of the hydrocarbon chain and replaced the carbon with oxygen, and the carbon that was next to it got double bonded to oxygen as well. So esters, like polyester, are usually very long polymer chains. They can also be smelly, aromatic, tasty smelling hydrocarbon or organic functional groups, compounds. Amines. Amines are really important because they're part of our amino acid structures, part of our amino acids in our DNA that help us produce proteins. Well, our DNA doesn't have amino acids, but our DNA codes for amino acid groups, which then are chained up together in a polymerization reaction to produce proteins. So amines are where we've changed from a carbon to a nitrogen, and it now has a different function. And amides are very, very rare. Honestly, I haven't seen many of them on the reagents or on our tests. It's basically where you replace a carbon with a nitrogen, and the carbon next to it has a double bonded oxygen on it. So amines are rare, but anytime you see these particular arrangements of carbon or nitrogen, oxygen, fluorine on a organic molecule, it's got a functional group. The halides are the first class of functional group. It's when a halogen, such as fluorine, chlorine, bromine, or iodine, replaces a hydrogen in an alkane. Alkene or an alkyne, I guess. Same rules as naming the hydrocarbons, except you must state the location of the halogen along the chain. So we start with the lowest number of the chain, and we label it up from there. So with this one, we're taking the name chloropropane. So we know it's prop, metheth prop, 3 carbons, ane, so there's no double bonds, and on the second carbon, we've got a chlorine. So let's do carbon, 1, 2, 3. There's the 3 chloro. I'm sorry, 3 carbon, 2 chloro for Cl, and then we fill up everything else, all the hydrogens out around, to fill up the bonding sites on carbon so that each carbon has 4 covalent bonds. So we've got 2 chloropropane. Let's name this next one. So we find our longest carbon chain, 1, 2, 3 carbons long. So metheth prop. So we know we've got prop is the root word for our hydrocarbon chain. There's no double bonds, so the suffix is ane, like the alkane homologous series. And then let's see, on the second carbon, we have a branch and a halogen. So we're going to say 2 fluoro, 2 methyl propane. 2 fluoro, 2 methyl propane. Because on the second carbon, we have the methyl group and the fluoro. So the number 2 signifies where those particular functional groups are. 2,2,3 trichlorobutane. So butane is the parent chain. But is for 4 carbons. ane means there's no double bonds. So the 2,2,3 means trichloro. So 2, 2, 3. So there's 2 chlorines on the second carbon and 1 chlorine on the third carbon, 2, 2, 3, and we fill everything else up with hydrogen. Just for clarity, I'll switch colors, and no, I went from the right to the left to number my carbons this time. If you went from left to right, you would have this entire image flipped. Let's see if we can flip it. Left to right. You would have that, except this would also be flipped. And it didn't quite work right, so let me just move on. How about that? Alcohols. One or more of the H's on a hydrocarbon chain is replaced by an OH. We call it a hydroxyl group. The E ending on the hydrocarbon is replaced by an OL. So all alcohols, their names end in "ol." They must also state the location of the OH with the number in the chain. Organic acids also have an OH in their functional group, so be careful. You're going to have to look for that. So 1-propanol. Prop, metheth prop, that's 3 carbons. The first carbon has the OH group on it because, you know, there's the OL and it goes on the first. And then we fill everything else up with hydrogen so that carbon has 4 covalent bonds to each carbon. There it goes. This next molecule, let's count the carbons. We want the functional group to be on the lowest number, so we'll start from this direction. Let's find our root for the hydrocarbon backbone. That's 4 carbons, so that's but. And we see this functional group here is an OH, and it's on the second carbon. So we call it 2-butanol, butanol. the OL, and the 2 are for the alcohol group, where it is located. Okay. Moving on here. Primary alcohols. What are those? This is when the alcohol is located on the end of the hydrocarbon chain. Example, the 1-pentanol. So this is the first carbon in the chain. Pent for 5 carbons. OL and 1 for the fact that it's got an alcohol on the first carbon. So there's our alcohol on our first carbon, and that's a primary alcohol. Secondary alcohol, it's attached to the carbon that's attached in the 2 other carbons in the chain. So for example, these are super condensed structures, but there's a 2nd, 3rd, 4th, 5th, and 6th carbon in the chain. So this is a secondary alcohol because the OH group is on the 2nd carbon. 2-OL, that's what it is. Hexa means 6 carbons total, which is what we have in this particular condensed structural formula. Tertiary alcohol. This is when the OH is attached to carbon, which is attached to 3 other carbons. So if we look here, 2-methyl, 2-propanol. So we've found that prop is our parent chain. So 1, 2, 3. On the 2nd carbon, we have a methyl group right there. And on the 2nd carbon, we have an alcohol group right there. So there we are. 2-methyl, 2-propanol. The molecule. Dihydroxyalcohol has 2 OH groups, so these are increasingly rare, but we kind of name it the same way that we were calling out where the double and triple bonds were in alkanes. We put the numbers out front. Ethane for 2 carbons. Count them up, just make sure we got them. 1, 2 carbons. And then 1, 2. Diol. Di means 2, OL means alcohol. So the 1st and 2nd carbon have the alcohol groups. That's how we know what the structure is from the name. So we're scrolling on. Trihydroxy, guess what? 3 OHs coming off the carbon chain. So we look here, we see we got propane, triol. So we have propane, metheth-prop, carbon, carbon, carbon. So we got our prop taken care of. Triol means we got 3 alcohols. 1, 2, 3, triol. So it doesn't matter which direction we start counting in. I'm just going to, and it doesn't really matter if you put these over and under or all on one side, top or bottom, because these molecules are 3-dimensional and will rotate in space. And the bonds actually rotate themselves too, but that's for advanced chemistry. So there we go. 1, 2, 3, propane, triol for 3 alcohols, 1 on each of the carbons. 1, 2, 3. Again, we're focusing on the functional groups. That was alcohols. Ethers. Ethers are like a link in the chain. Look for O bridging 2 hydrocarbon chains. Name the 2 branches off the O, then add ether to the end of the name. So anytime you see a name with ether in it, or at the end of it, you know that it's going to have an O branching between or bridging between 2 hydrocarbon chains. And the hydrocarbon chains are named according to our naming rules. So one chain in this first example, methyl, ethyl, ether. Well, we know we've got an ether, so we got an O in the middle. One side of the chain's methyl. Meth means 1 carbon, C. The other side of the chain is ethyl. Eth means 2 carbons. And then we saturate it all with the remaining hydrogens. Oxygen only forms 2 covalent bonds, so it does not get any hydrogens. Carbon forms 4, so we have to fill it all up with hydrogen. So in this case, methyl pertains to one side of the chain, ethyl changes to the other side of the chain, and the ether means the oxygen in the middle. Now, there's a couple ways to name this next one. We'll do the di terms. So we've got an O in the middle, so we know the last name's ether. And then so we have to name the 2 hydrocarbons in side chains. This first one's got 2 carbons. This one's got 2 carbons as well. 2 carbons prefix is eth, and we add the YL. So 2 So we could call this ethyl ether, or we could call it diethyl ether. I'm going to go with diethyl ether. Diethyl ether. That's exactly the same stuff that used to be used in surgery back in the 1800s. The unfortunate thing about this is super flammable. It goes boom. And back in the 1800s, they didn't have electric lamps in the operating rooms. They had candlelight. So you can imagine there were plenty of surgical explosions when ether or diethyl ether was being used as an anesthetic. Now, butyl propyl ether, this last one, we know we've got an ether, so we got an O linking two chains. One side is butyl, meth, eth, prop, but, 4 carbons, 1, 2, 3, squeeze the 4th one in. Propyl is 3 carbons, 1, 2, 3 carbons. Prop and but told me how many carbons. And then I saturate it all up with the remaining hydrogens, which becomes cumbersome when there's so many, which is why we came up with condensed structural formulas, so that chemists wouldn't be spending their entire days drawing hydrogens off of carbons. Aldehydes. Aldehydes are a class of compounds that are usually nice preservatives. The carbonyl group, carbon double bonded to O is the carbonyl group, is found at the end of the hydrocarbon chain. And E at the end of the alkane is replaced by Al. So aldehydes, names end in Al. That's it. Not OL for alcohol, but Al for aldehyde. Very similar to ketones, so beware. We haven't seen ketones yet. So let's look at propanal. Prop means that we've got 1, 2, 3 carbons. Anal means that the last carbon has this C double bond O to it with an H hanging off the side. Fill up all the carbons bonding sites with hydrogen, and we have ourselves propanal. There's the aldehyde group that goes with the Al at the end. Let's look at this next one here. So we have a 5-carbon chain. 1, 2, 3, 4, 5. Now, aldehydes are always at the end of the chain, so we don't have to tell 1, 2, 3, 4, or 5. We can just say what the name is. So we've got meth, eth, prop, but, pent. So pent is the root of our hydrocarbon chain. And the aldehyde is here. And so penta and Al, pentanal. Pentanol. Pentanal. Not pentanol, pentanal. Not so tough. Ketones. Carbonyl group, C double bond O, is located in an interior carbon atom. So aldehydes, when the carbon double bonded oxygen was on the end of the chain. Now we're going to see how that could be at any point in the middle of the chain. You got to tell us the carbon double bonded to oxygen location in the name. And we have the names that end in -one. So ketones have names that have an ending with -one. So alcohols was OL, aldehydes was AL, ketones is -one, ethers had the name ether in it. Okay? So this compound, seeing table R, 2 pentanone. So we know penta means 5 carbons. So we got our 5 carbons taken care of. -one means that there's a ketone in it, and the 2 means that it's on the second carbon. So we'll just do the second carbon there has the double bond, and then we fill everything else up with the hydrogens so that the molecule is saturated. This carbon already has 4 bonds in it, so it doesn't get any more. And we fill up the rest with hydrogen. And the ketone is like, it's kind of a little bridge. It's like a keyhole. I don't know why I think of that, but it's like a key and lock in the middle of the chain. Let's look at this next one. We have a ketone right there. So we know the end of our word is ONE. And we have 3 carbons long. So that's 1, 2, 3 carbons. That's meth, eth, prop. So we got propanone. propanone. Now we have to tell us which carbon the ketone is on, and it's on the second carbon, so it's 2-propanone. 2 for the carbon, one for the ketone, and that's where it goes and looks like. Organic acids are things like vinegar. And the way we find those is we look for a C double bonded to O and with an OH hanging off the same carbon. So an organic acid is actually a combination of an aldehyde and an alcohol, if you really want to think about it. Organic acids do generate H plus ions in solution, so therefore they are electrolytes. They're weak electrolytes, generally speaking. So, examples, propanoic acid. The name that is going to give it away every time, it has acid in it. So what we're going to do is we look and find our root, our carbon backbone, prop, meth, 3 carbons, anoic acid. So that tells us it's an organic acid, and it's always on the end of the hydrocarbon chain. And then we fill up all the other carbons with hydrogen. Propanoic acid. There's the organic acid functional group. This next one, we've just got 1 carbon, so we know it's meth anoic acid. There's no number that you have to put on here because there's nowhere else for that organic acid functional group to go. Esters, trickiest of the functional groups. It's like a combination of a ketone, and an ether. They have the ending of their name is O8, anoate. And the way that it works is the first word in the name, according to the branch coming up the O inside the chain, last word in the name corresponds to the number of carbons on the other side of the chain. So we have carbon double bonded to O with an O on the side. So that's the O8. That's how we know we have an ester. The first part of it is going to have ethyl. So there's 2 carbons on that side. 1, 2. And then butanoate is the other side. It has 4 carbons because that's 4 carbons for but. So many hydrogens to write in. Goodness. Let's try this one. 1, 2, 3 carbons, propyl, meth, anoate. Propyl methanoate. And let's try, look, propyl methanoate. Just going to do this one, trying to get through these here. I know this video is going quite long. I don't think I screwed that one up. Amines. Nitrogen is alone with hydrogen seen within the carbon chain. Change E on the end of a hydrocarbon to amine. So the names all have amine in them, and they all have this nitrogen in the middle of the chain. Let's get a little more room here. Propanamine. First carbon's got the amine on it. So prop, 3 carbons with a nitrogen hanging off of it. Fill everything up with hydrogen. My goodness. 2, pentanamine. Penta, 5 carbons. The second carbon has a nitrogen on it. So we fill everything else up with hydrogen. My goodness, all these hydrogens everywhere. So let's see if it's in the middle of the carbon chain, what do we do? So we'll call this two propylamine. I'm not going to see these very often, so let's get to the end of it. Amides. Not only an end in the carbon chain, but also see a carbonyl group attached to the nitrogen. So propanamide, you've got prop, 3 carbons, nitrogen, the double bond on the oxygen. No, sorry, made a mistake. Double bonds on the carbon next to the nitrogen. Fill it all up. Butanamide. And you're going to see these very, very rarely, if at all. Butanamide. Bonuses. See if you can figure those out. Methyl ethanamide, I'm really going to not worry about them too much. Functional groups with branched hydrocarbons, the same rules, you just combine the rules. So 2-methyl pentanal, ANAL, is an aldehyde. So penta, longest chain, is 5. It's got an aldehyde hanging off of the end of it. So this is a HO. And the second carbon has a methyl group hanging off of it. So we just kind of start building up the rules and lay them on top of each other, and we get more and more complex molecules, which is what organic chemistry is all about. My goodness, let's see what we got here. We got 3 carbon chain is the longest. So that's prop. It's an alcohol on it. Propanol for alcohol. And there's a methyl group on the second card. So 2-methyl propanol. All right. So I'm not sorry for the long video, because that's what organic's about. The functional groups are complex, and we'll have to practice a lot of them. Basically, you should be able to identify using table R which functional groups present in a molecule, and use some of the basic naming nomenclature rules to start drawing and naming these organic compounds. Lots of practice on this, so don't sweat it if you didn't really get it after just watching this video. Thanks. Talk to you later.